Continuing on, we're going to talk about combustion reactions. So combustion is the reaction of any substance with O2. So we talked about reactivity patterns previously, and those are different ways that we can characterize different types of reactions, how compounds and elements come together and change in different ways. So starting with combustion reactions, we're going to move into talking about types of reactivity based around particular types of compounds, or even in this case, specific elements, right? Combustion is a reaction of any substance with oxygen. And so one of the goals here is that we're going to want to be able to see, well, if there are predictable patterns in how different substances react, we can start to make predictions about how chemical reactions will proceed without needing to do those chemical reactions. So combustion, reaction of anything with oxygen. So it gets its own name because this is an extremely common type of reaction. Here are some examples up here of showing reactions of things with oxygen. So match tips have phosphorus in them. Phosphorus is really good if you rub it at just spontaneously lighting or igniting. So it lights on fire, then that gets hot, the wood of the match lights on fire. Burning propane, we have seen this reaction a handful of times now. And that's a really useful reaction. We burn propane as fuel, either using it in stoves or on gas grills. And so one of the things we can see about combustion is these reactions are usually very, very energetic. There's a lot of energy released that we use for practical purposes. Sometimes that aggressive energy that's released is not used for practical purposes, but something we should be aware of. For example, the fact that hydrogen gas is extremely flammable, extremely dangerous. And so these ideas that, we want to be aware, we don't want to fill our blimps with hydrogen gas anymore, because if a fire starts, it will quickly become a total catastrophe. Not all combustion reactions are quite so energetic or quite so showy, at least in their energy. Rust is an example of a combustion reaction where you have iron reacting with oxygen in the air to produce iron 3 oxide. That's rust, and so that is a degradation process. Again, it's a combustion process. It happens really quickly, or it happens really aggressively. It's just a bit slower, and there's not as much flame involved. But we spend a lot of time and effort protecting iron from undergoing this process because it is degraded, right? It corrodes the iron. It loses its good properties associated with being a solid metal. So the thing about combustion reactions is there are always 2 reactants. One, whatever substance is undergoing combustion, and oxygen, right? Those are always the 2 reactants. And one of the reasons why this gets its own name is because we can always predict the products. Whatever substance is undergoing combustion, every single atom type in that compound or element, whatever substance it is, will form a product that's an oxygen-containing compound. So whatever substance you have, whatever atoms are in that, you're going to make one product for each atom type. It's going to be that atom combined with oxygen. So maybe we'll look at some examples, parse out how that works. So let's write chemical equations for the combustion of each of the following substances. I have magnesium solid and C2H4 gas. That's called ethylene. In this case, I want a chemical equation, so I know what are my reactants, what are my products is always going to be kind of my go-to strategy for coming up with that. In the case, because it's a combustion reaction, I know the reactants are whatever's undergoing combustion plus oxygen. When we see this word, combustion, we want to be thinking oxygen is one of my reactants with whatever I'm given. You do need to be given the other thing, so for this case, magnesium and ethylene, but it is implied that the other reactant is oxygen. So then my next question is, well, what are the products? What I do is, whatever atoms are in that reactant that's undergoing combustion, I form a compound for each of those atom types of that atom with oxygen. So in this case, I would have magnesium. So I would make there's only one atom in this, it's elemental. So I'd make a product of magnesium and oxygen. For C2H4, I have carbon and I have oxygen. So for each of those atom types, I need a product. So I'm going to end up with 2 products for the C2H4 molecule, one is the carbon and oxygen compound, and one's going to be the hydrogen and oxygen compound. Let's write it out, see what it looks like.
So we know when we're dealing with combustion, we've said that what that means is we have our substance that's undergoing combustion, in this first case, magnesium. So what we would do is we write out our equation. We know that there's going to be magnesium involved plus O2 gas. And that O2 is always indicative of combustion. Okay. And so then the question is, that is the entirety of our reactants. And our reactants are always going to look like that. And so whatever is undergoing combustion plus oxygen. So we've got those two. So then the question is, what do we produce? Okay, what is the product? And so for our product, what we're going to do is we're going to take all of the atoms in what's undergoing combustion, and we're going to make a compound of them with oxygen. So I need to make a compound out of magnesium and oxygen. Okay? And so we need to think about, well, what is that going to be? What's that going to look like? Well, we can use our periodic table, and we can look up that magnesium is a metal and oxygen is a non-metal. And we know that when a metal and a non-metal form a compound, that compound is going to be ionic, right? Magnesium's over here, that's on the metal side, oxygen's non-metal. So we're making an ionic compound. Question becomes, what charges then are they going to make? We know magnesium as a metal is going to be a cation, so it'll be positive. It's in column 1, 2, so magnesium will be magnesium 2 plus. Oxygen is in column 6, so 6 over here, so this would be 0, minus 1, minus 2. So that means we have O2 minus. We can take those charges, move them down. We would then get Mg2O2. Those are both 2's as the subscript. That can simplify to Mg. Oh, okay, so the substance, the product that we will make is MgO, magnesium oxide. When it comes to dealing with combustion, we generally are mostly concerned with what the product is, what that substance is. We don't necessarily, the phases aren't going to be as important. This is an ionic compound. Ionic compounds are solids at room temperature. It's very hard to melt them into liquids or to boil them for that matter. So magnesium oxide is going to be a solid. You could also look that up, what it is, what the phase of that is. But so we have that. I won't worry too much about getting a solid. What's more important is that you get MgO. There is also another very important part of completing this reaction equation, and that is balancing. This is not balanced as written. Magnesiums are good. I got 1 and 1, but I have 2 O's, 1 O. That is not going to work. In order to balance this, I need to put a 2 in front of it. So then I have the 2 oxygens in that one molecule. Each of these MgOs only has a single oxygen, so I need 2 of them. All right, I put the 2 out front. It affects everything. All right, so that means my magnesium, I now have 2 magnesiums. Over here, I need a second magnesium. So 2 magnesium atoms react with 1 O2 molecule to make 2 MgO formula units, right? That's because it's an ionic compound. So our answer is going to be 2 Mg plus O2, give me 2 MgO for my combustion of magnesium. C2H4 is then ethylene. We know the start is going to be the same. My reactants, same idea because it's still combustion. C2H4 gas plus O2 gas becomes some sort of product. So when I now look at the formula, I have carbon and hydrogen. So I have 2 atoms in that reactant. So I'm going to make 2 products. One is going to be a carbon and oxygen compound, and the other one is going to be a hydrogen and oxygen compound. So I have carbon and oxygen, and then I also am going to have to deal with hydrogen and oxygen. And so if we look here, these are going to be covalent compounds. Carbon and hydrogen are both nonmetals. So these are going to be covalent compounds. We cannot predict them like we did with the ionic, where we could use a periodic table, predict charges. We can't do that. What we can do though is basically, it's going to be what the most common oxygen compound of each of those is. So what compound is carbon most likely to make with oxygen? What compound is hydrogen most likely to make with oxygen? And for most things like these, you can kind of just think about what compound do you most interact with? The most common hydrogen and oxygen compound is going to be you deal with every day. There are plenty of kind of obscure ones, but the most common one that you deal with every day is water. So you're gonna make water. If hydrogen is gonna form a compound with oxygen, if it has any choice, hydrogen peroxide is a thing, but water is more stable. That's why water is the most common. Carbon and oxygen come together to produce what you are currently breathing out right now, carbon dioxide. So whenever we have a carbon-containing compound that undergoes combustion, one of your products is going to be CO2. If there's hydrogen undergoing combustion, you make water. That is always true. That is just a property of these combustion reactions. So our products are going to be then CO2 plus H2O gas. You'll note again the phases. Carbon dioxide is a gas at room temperature. Water is normally a liquid, but the reason why it's a gas here is this is burning. These combustion reactions generally produce a lot of heat. Again, I wouldn't worry too much about the phases. What's more important is that you got water down. That is far more important than getting the phase for it. Okay, so we got that. Got ethylene, oxygen, ethylene and oxygen combined to give you CO2 and water. Wonderful. We've got predicted our products. We do not want to forget to balance. This is not a balanced equation. I have 2 carbons right here. That is a single carbon atom. That needs a 2. I have 4 hydrogens. This is only 2 hydrogens. So this also needs a coefficient. Another 2. Then for the oxygens, I have 2 oxygens on my reactant side. For my product side, I have 2 carbon dioxide molecules. So 2 times 2 is 4 oxygens. I have 2 water molecules, each with 1. 2 times 1 gives me 2. So I have 4 oxygens, 2 oxygens. This is 2 oxygens over here. So this, I have 6 over here. 2 times what equals 6? 3. So for the combustion of ethylene oxide, or ethylene, sorry, C2H4, it's going to be 1 C2H4 molecule reacts with 3 O2 molecules to give me 2 carbon dioxide molecules and 2 water molecules. And so any sort of covalent compound, we would need to theoretically memorize, like say nitrogen, phosphorus, sulfur, all these non-metal elements. There is a most likely oxygen compound they make, oxide that they make. Really functionally, we just need to remember that carbon is carbon dioxide and hydrogen is water. This reaction where you have a compound that's made of carbon and hydrogen reacting with oxygen, most fuels that we burn look like this, and when we burn it, we're reacting it in combustion. And so if you this carbon and hydrogen, remembering that you're going to make carbon dioxide and water is going to be that's the most common combustion reaction you see. Metals making the oxide, making an ionic compound, and then also carbon and hydrogen compounds making CO2 and water. This is why you breathe out water and CO2. Your body is doing work on this. That's why cars, engines, right? Combustion engines, internal combustion engines are run on this process. It's a different carbon hydrogen compound, but you make CO2 and water. That's why doing all those processes release carbon dioxide and water, because it's all this combustion of carbon and hydrogen containing compounds.
Participation 611, question 3. Write the chemical equation for the combustion of C7H16. You don't need to worry about phases. This is the third question on participation 611, due Thursday, June 11th at 11:59 p.m. over on Blackboard. Link to the assignment is right below the links to these videos. Again, write the chemical equation for the combustion of C7H16. And again, if you're writing a chemical equation in the Blackboard text editor, don't worry too much about formatting, superscripts, subscripts,
arrows. If you're handwriting it, want to get that stuff correct, but don't worry too much about typing it. You can get subscripts and stuff in there, but it can be a little tedious to insert all of those. All right, 3 questions on participation 611. We had a test, so I tried to go a little lighter today. Speaking of, if it's not Thursday yet, make sure you come at 9 a.m. for the test. Get the pre-lab technique and notebook set up for reactions of copper. Otherwise, the rest of this week, you got another set of videos for Friday, continuing chapter 4, post-lab due Saturday, and homework Saturday. And again, we have the lab group 1 evaluation on Sunday. We're going to change lab groups for next week. So for the reactivity patterns, you'll be in a new group. I will set up that group on Sunday and set up the notebook pages for reactivity patterns for your new group. So please wait until Sunday to look at setting up the notebook. If you have any questions about anything, let me know. Otherwise, see you around. Bye-bye.